Welcome back. Today we are going to look into the final components of power, and that is called the leakage power or also static power. We already look into dynamic power and short circuit power. So let's dig into it. But keep in mind that these first two are the components of powers when switching of state from logic 1 to 0 and 0 to 1 happens. A short circuit is not about charging or discharging the capacitor, but it's a direct path from VDD to ground and happens when both NMOS and PMOS are on. So what is leakage power? And you might have heard that this is a very significant part of modern day power, or very important to consider it. It has two further components. So let's look into the first one here. Um, yes, there's too much stuff on this, but follow me. If you follow me, I'll take you through each one of these one by one. So if you remember, this was the reverse bias depletion region. And I explained this, that this is like a, this is like a diode. And when I look at a diode and explain, okay, how is the depletion region happens. So let's revise it a little bit. You can always watch that video in detail if you want to understand diode operation, because this is really a diode. This is drain, this is bulk. Drain, bulk is always grounded. This is NMOS, by the way. Source is grounded. Drain is go from 0 to VDD, 0 to VDD. So this P, as remember I told you, if it will be followed by when P is at higher voltage, and this N, these are N regions, they are at negative, lower voltage. And whenever that is not the case, it's in a reverse bias. So, but different stages of reverse bias. When it's a very strong VDD applied, it's a pretty strong reverse bias. And the pressure region will widen. Or you can say that these some of the anyway. Let's look into it. It'll be a good revision. So understanding this diode here or reverse bias of it is very important, because knowing this one will help you understand how we can reduce this power. So let's say this is PMOS, PN, and this is P area. A lot of holes. Holes are the majority carriers. This is N area, and this is where electrons are majority carriers. So let's assume this is not connected to any voltage. In the equilibrium condition, what happens is initially, as soon as you bring an N and P together, right there from this side, holes will try to get here quickly, combine with the electrons here, right? So as soon as they leave, okay, you are left behind a kind of negative charge. And similarly, electrons at the boundary. See, when you bring them together, first the people at the border, they do the migration. I think I gave that analogy of immigration. They leave the country. They leave the country. So as soon as these electrons leave, they leave behind a positive charge. So as soon as that happens, these negative and positive kind of things kind of stuck with each other. They create a wall here that stops further flow. That's really the depletion region here. And you can think of that, okay, the small this is, right? Or how strong our positives are aligned here and here. That really put a lot of pressure on this. There will be a stronger wall. If there is a force which is kind of attracting this negative things toward this this side, right? It's kind of breaking this. Or if there is a very strong force on this side, this can also break this barrier. So this barrier is important here. We rely on that. We don't want to have electrons free carrier. So there are electrons. This is N. This is holes. We don't want electrons to flow here. We really wanted to have a nice kind of barrier here. The whole idea is that to have electrons only in this channel this flow, because these are really the electrons that we are controlling through gate. The better control we have here, the better transistor is. And if current starts leaking here, you will see even when you don't want any current flow, some current is flowing through here. You're finding a path here, finding a path here, finding a path here. So your electrons are wasted, your voltage is disturbed and all that. So it's no longer an ideal switch that you really wanted. So it's really important that we have this wall here, this barrier here. We can, this is the way to create walls at the transistor level, to kind of create this depletion barrier. But what actually happens that this junction here is a stronger function of temperature. So even the junction temperature when transistors are operating, they're not even at room temperature. Typically the voltage is temperature is 80-85 Celsius. So we're pretty high temperature. And what happens, these guys start vibrating, you think of that. They start moving. So your depletion region is really disturbed. So current start sneaking out. So when we connect it, an actual P is kind of grounded, right? And this D is drain is at higher voltage. So this higher voltage starts pulling electrons, right? Start pulling electrons from this side. And this negative lower potential start getting holes from this side. There are electrons here, they start going there. Or you can even get electrons flowing from this side into this. This kind of drifting thing can happen too. So the bottom line is, the main thing for you to understand and remember is there's a depletion region, and we don't want any flow of electron, whether it's a diffusion or a drifting type of activity. But it starts happening. And that is one component of that leakage. The transistor is leaking. I hope I've explained it well. So you must be wondering how we can reduce it. So right away, it gives you a lot of things to think about. What is the first thing you can think of? Okay, temperature, yes. If we can somehow make this device cooler, it doesn't get a lot of temperature here, then this leakage current will be less. Okay, great. Something else you can think? The higher the reverse voltage here, the stronger this voltage here, we will disturb this area. Okay, it will really push these guys. If positive voltage, there are electrons here. These are really kind of go back here. These guys will start moving here. So we don't have very extraordinary high voltage here relative to the depletion region. And then what else? If we have a lot of electrons here, okay, then and a lot of holes here, these electrons over here will start moving here, and it holes here will also start moving here, or holes here. There will be a lot. This thing might be start breaking. Actually, you think of that. These electrons are really going in this way. These can go in this way. This can break this apart. These can go that way. You can break that apart. So a lot of unwanted activity will happen. Just remember that. So this, if there are less electron, or the area of this thing, kind of that one that really faces this depletion region, if that is small, that's also another way you can really make a less impact on this barrier. You don't want to break this barrier. Okay, so here are some of the things I mentioned, and some of the things that you might hear me more talking in very soon coming videos that I will talk about scaling or short channel effects and all that. But let's try them. The first thing is shallow drain source, smaller area, which I mentioned. If you have this barrier kind of a smaller area here. This thing is smaller. Or you start creating the main area that facing the channel area is small, and then we make it longer because we really want to have a less impact in this area. See, even if there's a leakage, there will be less leakage here, or maybe we can, because strong voltage is here, this is the area we want to have least impact. We don't want leakage anywhere, but this is really the more interesting area. Voltage, I already mentioned, less voltage. Temperature, we already talked about. Retrograde wells. Okay, retrograde well. So this is the well. So well, you will see that in 250 nanometer, 180 nanometer, 130 nanometer, and going down, the engineers or scientists working on these transistors, they start playing with the doping concentration. But is this doping concentration here? It's the same thing here. You say number of electrons. Here, there are number of holes here. You can also address this number of hole here so that in this vicinity of the channel or in the top layer, you have less holes. So less hole mean there is less possibility, even if there's a strong force, that holes will go there. So it's kind of retro backward or back, and grade is kind of doping level. So what you do is you have in this area you have low doped, low quantity of holes, and at the deeper side you have a higher quantity. So it affects its less here. So those are some of the things that engineers started, or process engineers started doing with the well here. And I think I might have a little bit more detail. So I hope I explained these well. So just the bottom line is we want to have this leakage less. Okay. Next component is the typical one. So let's finish this video here, and we will do the second one later. Okay. Thank you so much. See you next time.